Thanks everyone for coming today to check out my talk. So there's been a lot of discussion in the field about how we can improve power in order to improve fMRI reproducibility. So there are a lot of different angles on this issue, and people have suggested a number of different paths forward. But I think just as we've come up with, an avenue forward, this has raised a number of additional questions about how we can actually achieve some of these goals. And a lot of these goals require us to be able to estimate power, specifically in the context of fMRI, which can be deceptively difficult. So today I'm going to talk about a path towards allowing us to better estimate both effect sizes and power for fMRI study planning. And this has two parts. The first part is to understand what sort of effects we might expect for typical study designs. And the second part is to develop power estimation procedures that are specifically tailored towards fMRI for these typical studies. So most of this talk is really going to be about this first part. So I'll start by saying how I define typical studies. Here, a study refers to any analysis to estimate the effect of a unique phenomenon in a particular data set, but there are multiple data sets used here. Specifically 5 large, which is N larger than 400 subject studies. 6 actually there. And the studies that I'm using here are chosen to reflect very typical study designs in fMRI. So I'm using 2 common mapping modalities, functional connectivity and task-based activation, and then 3 types of effects. One is a task versus rest contrast, which is a within subject design, and then 2 between subject designs, a group versus group contrast, and a correlation with behavior, phenotype, demographic variable, etc. So in total, I have 45 studies, which lead to 45 effect maps. And this is what these studies look like. So now that we know which studies we're using, we can talk about how we're actually measuring effect sizes here. So I'm converting everything to Cohen's d in order to facilitate comparison across studies. One thing I'll note here is that the sort of standard conventional conversion from R to D assumes that actually we're looking at the effect size associated with a change in X of 2 standard deviations. I'm just going to stick with that particular convention, but note that if you chose a different change in X, that could also differ. And I also want to note that it's kind of difficult to compare the same Cohen's d effect sizes across within and between subject designs. Notice that these have different implications for the number of subjects that you would need. For example, for a small Cohen's d effect size, you actually need 4 times the overall number of studies across both groups for between subject design as a within subject design to detect this with 80% power. But with all that in mind, we are going to use Cohen's d moving forward. All right, so we'll start by looking at, and for most of this talk, I'm going to talk about these simultaneous confidence intervals for Cohen's d. And what that means is that 95% of all experiments should contain the true value across all edges and voxels in these simultaneous intervals, sort of like a multiple comparison correction for a confidence interval. And I'm going to start by just showing some representative studies from the HCP for simplicity, and then we'll look at all possible studies. So in the between subject context, here's a correlation with behavior or demographics. So here we find 100% of these effects contain 0, so they could possibly be 0. Here for a group contrast, in this case it's female rest versus male rest, we find that 80% of these effects could be 0. In the within subject context, we can look at a task rest contrast and functional connectivity, where we see that 30% of the effects now could be 0, so a smaller number of effects. And in a task-based activation, working memory compared to essentially a rest, about half of those effects could be 0. So overall, I want to point to that for the between subject case, most effects could essentially be 0. Of course, there's, as many people have talked about in biomedical research, we probably wouldn't expect anything in the, population to actually be zero, but it could be trivially small. And then we would likely expect stronger effects for the two sample compared to the correlation context, and for group contrasts, that's actually the same thing. And then for functional connectivity compared to activation. So those are just the representative studies. We can see what this looks like across all studies in the effect database that we're working with today. And I'm actually going to convert these full confidence intervals to just conservative effect size estimates. So what that is the smallest or closest to zero part of the confidence interval. So that kind of reflects like our most conservative possible estimate of the effect size. And for these conservative effect sizes, it's still the same process as before about, what could be zero. For correlations, we find that, more than 99% of these across studies could be zero. For the two sample test, we have a few more effects that could be non-zero. So, but overall for between subject, most edges, most effect sizes at the edges could be zero. I also want to note that we were only able to detect correlations or substantial non-zero correlations in the UK Biobank, which has more than 10,000 subjects. And we also see quite a bit of variability across the two sample test contexts. And for the within subject context, we see, as before, now 33% of these effects could be zero, so smaller number. And then 76% of activation mapping effects could be zero. So overall, for within subject, we see a substantial number of effects that are now likely non-zero. So now I'm going to move on to talk about the maximum effect sizes across each of these studies. So for the correlation context, the maximum conservative effect size is a small effect size of 0.2 across all studies. That's the single edge with the largest effect. The single edge with the largest effect in the two sample test context, the group contrast, is a medium effect size. So again, across both these contexts, the very largest conservative effect size we observe is medium. And then for the within subject within subject context, we see that the max conservative effect size for functional connectivity is actually very large, Cohen's d of 2. And the max conservative effect size for the activation mapping context is also quite large, not too far from 2. Note that a large Cohen's d is defined as 0.8. So here we see, max conservative effect sizes can actually be quite large. So overall, I would say based on these results and just looking at the conservative effect size estimates, to be most conservative, I would recommend planning for most effects to be, very small between subject, maybe a bit bigger for task-based activation, to potentially much bigger. And then for functional connectivity, task-based contrasts within subject, you might see very substantial effects. Again, this is sort of the takeaway from this particular way of looking at these effect maps, really just looking at these conservative arms of the confidence intervals. There are other ways you might want to think about planning for, study design, looking at the full confidence interval, for example, looking at, how big the effects could get to. But just as a start, I think that this is one potential way to think about, planning for conservatively for your study. And then, as some of our intuition might have already told us, and as we said before, we see, that within subject designs are substantially larger than between subject designs. And then we see, task-based functional connectivity, just these simple contrasts tend to be greater, larger effects than these activation-based effects. And here's one concrete illustration comparing these 4 different categories. So to detect the single max conservative Cohen's d, and this is just a single test, no multiple testing correction, as if you knew that you were going to see just, that maximum Cohen's d. For a correlation-based study, you would need 400 subjects per group, or 800 subjects in total, to be well powered to detect that effect. For the 2-sample context, you would need 68 subjects per group, so about 130 subjects in total. But for the functional connectivity, task rest contrast, and for the activation mapping context, you would only need 4 or 5 subjects to detect that max effect for those contexts. Remembering, of course, that for the same Cohen's d, the between subject contexts on the left there typically need about 4 times the number of subjects. So just, 800 subjects compared, or 800 or 130 subjects compared to the 4 or 5, I think is pretty notable. And I highlighted it because of that. And really quickly, we're just going to look at how this varies across categories. For instance, clinical, cognitive, biometric, etc. So for the correlation context, we see that the largest effects occur in the context of age-related correlations, and also BMI, just because, the BMI and the ABC, even though the UK Biobank age correlation is the top correlation, when we look at a smaller data set compared to the UK Biobank, the ABCD, we see that we have more non-zero effects for BMI than age. So possibly, BMI has even larger effects than age. We have small but significant effects for fluid intelligence, memory, some of these, cognitive constructs. And then there's little evidence for effects, detectable effects in these samples for clinical and other cognitive effects, again, in the univariate context. In the group contrast setting, we see that, gender or at least I think biological gender, self-reported biological gender used in many of these studies tend to show larger effects. And again, little evidence for the clinical context. So minimal effects that we're able to detect here for some psychological constructs. And then in the within subject context, specifically for functional connectivity, we see, working memory being the best task. I'd say they're pretty similar across tasks here, so I wouldn't read into that too much. And then in the activation mapping context, social tasks tends to have the largest effects, gambling tends to have the least. There's different skews for some different studies, but overall, all tasks are fairly substantial and especially for functional connectivity, pretty similar. Now we're going to look a little bit more about the spatial distribution of some of these effects. So here are just maps for a meta-analytic estimate of Cohen's d for those studies that used that we processed with the Shen Atlas. Something that you can see right off the bat is that there tends to be some of this structure within the sort of canonical networks across a number of different contexts. You can start to see some of that structure in the biometric category. It becomes clearer with larger effect size for things like the cognitive, the task-based within subject context. And we can look at some of the other non-Shen types of effect maps. So UK Biobank uses ICA to define the nodes here. I don't have a mapping for that at the moment. I'm looking into it to see what the structure looks like, but that is a next step. I'm just showing this here for completion. And then for the task-based context, I've just taken the mean Cohen's d across the HCP tasks, which is the only data set right now that I have with activation maps, large data set with activation maps. And you can see that there's also clearly some structure there as well, some spatial structure. And potentially this could also align with some of the canonical networks. So some future directions for the effect mapping project. So there are more studies that are incoming. We are also particularly looking for activation maps in large and greater than 400 subject data sets. Another next step is to repeat these analyses using some of the broad scale and multivariate procedures that we've developed to estimate how effect sizes might change for those conditions compared to univariate effects. And then a big plan for this is to provide a typical effect map explorer, just a point and click simple app that you can see what effect sizes you might expect for a number of different very typical contexts. So all the studies that we have in the database. And I'm going to talk about more future directions actually in just a sec with the second part, which is developing tailored power estimation procedures. So here are those future directions. The overarching plan for this next several years is to create a power calculator that can provide some guidelines for a range of typical study designs and inferential procedures. So again, this should be point and click. You shouldn't have to provide any information other than information you already have. So, you know, what sort of condition you're using, whether you want to perform a univariate inferential procedure or cluster-based inference, for example, but there's no need to provide effect maps or to do any of the sort of estimation of power yourself. The idea is that we'll do some empirical benchmarking in the background before you even get to this page, and then you'll be able to use that as kind of a power lookup table. But yes, it should be very easy to use and with information that's readily available to everybody. And I think this sort of empirical benchmarking procedure can also be helpful for comparing new procedures. You know, how powerful would I expect this arbitrarily complex inferential procedure to be compared to some other existing procedures? So a quick summary. I would plan for conservatively, this is one way of looking at it, but you might plan for considerably smaller effects for between subject designs compared to within subject designs. I think there's also a lot of promise from what I've shown today and from what others are doing in using large open data sets coupled with empirical benchmarking for things that may be sort of arbitrarily complex data, complex inferential procedures to provide some practical guidelines, sort of a starting place here for what effects we might expect, and also a good way to understand the practical consequences. And finally, converging evidence from a lot of work in the field and also some of our previous work, coupled with the small effects that we've shown today, point towards a potential motivation to shift towards broader scale or multivariate inferential procedures. So I'd like to thank everybody in the lab who've been instrumental to helping get this data together and do some processing of it. Lots of amazing people. It truly is, you know, a team effort. And lots of other people, collaborators that have contributed to this work, some previous work, related work, which I'm very grateful for. The data sets, of course, without these, we would be nowhere, and my funding sources. And here I'd like to just let everyone know that I am now starting to hire for the NeuroPrism team at Northeastern. So please reach out if you're interested in positions at all levels. So thank you, and please let me know if there are any questions. If you're watching this, which I imagine many of you are, you can feel free to shoot me an email or reach out to me on Twitter. I'm happy to be contacted in any way you'd like. All right, thank you.